Good morning. No, good afternoon. Today we are learning about Lenz's law. Here's our learning objective. Lenz's law predicts the direction of the induced EMF and current in a conductor. The reference for this is page 146 of your textbook. And here it is. Come on. That's better. Okay, here it is on page 146. Success criteria. What you need to do here is make a note of the formal statement of Lenz's law, because we need to learn the words, and be able to use Lenz's law to predict the direction of the induced current. Okay, now this is a bit tricky to demonstrate and to understand, but we're going to have a go. So, Lenz's law says the following, that the direction of the induced current is such that it opposes the change in magnetic flux that produces it. So, it's about the direction of the induced current, and the key word here is that it opposes. So the induced current that's produced opposes the change in magnetic flux that is producing it. Now, let's see if we can show what that means. Here's our coil and magnet experiment. Now, if we set this up, we've got a magnet and we've got a coil. Now, I've put red and black wires on the meter. Red is positive and black is negative. Now, we remember that red is positive and black is negative with respect to conventional current direction. Now, unfortunately, we can't see the meter. There we are. There we can. Okay. Now, if I push the magnet towards the coil like so, did we see that? And pull it out again. I'll do that again. If we push the magnet in, can you see that the needle deflects to the right? Now, the needle deflecting to the right is a positive current, and that means that current is flowing in on the positive side and out on the negative. Now, here's the coil. On the coil, the wire is running around the coil in this sort of direction. In this direction, it's running around like that. So, if we draw the coil like so. Now, if the current is flowing from in to the positive side and out from the negative side, that means that in the coil it's flowing around this way. Okay, so that it goes out through the positive and in here. Now, that means that on the top of the coil, the current is flowing around like this. So it's flowing from top to bottom as we look at it on the top of the coil. Now, if that's the case, then we can use the right-hand grip rule to predict the magnetic field that will be set up around the coil. And it will look something like this. Here's the field lines going through the coil, and we can have a looped one as well. Now, the right-hand grip rule says that the fingers of the right hand grip the coil in the direction of the current, which is down the ways, and then the thumb will indicate the North Pole. So therefore, the magnetic field that is set up in the coil due to the induced current will produce a North Pole at this end and a South Pole at this end. In other words, field lines are running north to south like this. Now, the magnet we pushed towards the coil with its North Pole first. So the magnet was like this. Now, can you see that as the magnet moved in, its north pole was moving towards the coil, and the current that flowed in the coil was such that it set up a magnetic field with a north pole at the right hand end. Therefore, the magnetic field in the coil is going to oppose the movement of the magnet. It's going to try to repel the magnet and stop it coming into the coil. Now, what happens if we reverse the direction of movement? Well, when the magnet comes out of the coil, the current goes in the negative direction. That means the direction of the current has reversed. So in that case, what we would have is everything in this diagram reverses. So now the situation is this. The magnet is moving out of the coil. Come on, keep up. The magnet is moving out of the coil in this direction. We saw that the current moved in the opposite direction, so that means it's now flowing this way around the coil. If we use the right hand rule, then the fingers of the right hand grip in the direction of the current. The thumb gives us the north pole to be this end. Therefore, this end is a south pole end. So when the magnet is moving out of the field, like that, the current that is induced makes this end of the coil a south pole, so that it will attract the magnet and try to oppose the change that is producing it. It tries to pull the magnet back and stop it leaving the coil. So this is what we see by experiment. When the magnet moves into the coil, a current is induced because there's a change in magnetic flux inside the coil, but that current flows in such a direction to oppose the change in magnetic flux that produces it. It makes this end of the coil a north pole to oppose the motion of the magnet towards the coil. When the magnet is withdrawn from the coil, again, that's a change in the amount of magnetic flux that is linking the coil. In this case, it is decreasing. That induces a current to flow in the coil, but the current flows in such a direction as to oppose the change that produced it. So it makes this end of the coil a south pole, so that it will try to pull the north pole back again, and so oppose the change that produces it. Now, Lenz's law expresses this formally. It says that the direction of the induced current in any situation where induction is occurring is such that it will oppose the change in magnetic flux that produces it. Now, we have a nice little trick which can demonstrate Lenz's law in action in a different context. This is a copper pipe. It's just an ordinary piece of 15mm diameter copper plumbing pipe. It's got a little slit cut out of the side there so that you can see what's going on inside, but apart from that, that's all that it is. Okay. Now, and we have two little slugs, which are basically metallic with little plastic feet on the end. Now, if we take one of the slugs and drop it into the end of the tube like this, it will slide through. Now, we can just about get this into shot. Here it goes. Okay, and again. So that little slug shoots through. Now if we take the other slug and drop it, watch what happens. Okay, did you see that? Let's do it again just to prove that it wasn't a fluke. There it goes. Okay, and it drops out the end. Now, that one takes about 5 seconds to slide through the pipe. The other one takes less than a second. Why? What's the difference? Well, it's not magic, of course. It's physics. there is a difference between the slugs. Here's a paperclip. The paperclip is not very interested in that slug, but it likes that one. This one is a neodymium magnet. The other one is just a lump of non-magnetic stainless steel. So this is quite a strong magnet. Now, when this magnet slides down the copper pipe, and you can see it going, it's a magnet, so it has a magnetic field. Its magnetic field lines extend out around it through the sides of the copper pipe. The copper pipe is a conductor. In fact, we can think of the copper pipe as being made of a series of rings of copper all the way down, and each ring is like a little circuit. Now, as the magnet passes down, the flux lines around the magnet are going to cut through those little copper rings, and therefore you've got flux cutting going on, or a change in flux linkage, and therefore there is going to be an induced EMF in the copper. And if there's an induced EMF and a complete circuit, the ring, then a current can flow. These currents are called eddy currents. So really what's happening is, as the magnet moves down through the copper pipe, the changing magnetic flux, or the flux lines that are cut, induce little tiny eddy currents in the copper. Now, these currents obey Lenz's law. That is, they flow in such a direction as to set up magnetic fields of their own, which opposes the movement of the slug. And so the slug feels a force which tends to oppose its motion down the tube. The other slug is not a magnet, so it doesn't induce eddy currents in the copper, so there are no magnetic fields to slow its progress, so it just slides on through. So the slug is okay. Now, less than 3 minutes to explain the last bit. Lenz's law is an example of the principle of conservation of energy. It has to be, because suppose that, well, when you push the magnet into the coil, a current flows in the coil. Now, a current has electrical energy, so that energy has to come from somewhere. And where it comes from is you doing work by pushing the magnet into the coil. Now, if the current flows to oppose that motion, then you actually have to do some work. You have to push the magnet against the induced field into the coil. Therefore, the work that you do appears as electrical energy of the current, and the principle of conservation of energy is satisfied. If it were not so, if it were the other way around, and the induced current produced a south pole, then the magnet would actually be pulled into the coil without you doing any work at all. And it would be pulled into the coil and would actually gain kinetic energy. So you would do no work, and yet the magnet would gain kinetic energy, and since the magnet is moving and there's an induced current, there would be electrical energy as well. So therefore there would be zero input energy and yet output electrical and kinetic energy, and that would violate the principle of conservation of energy. So the other way around, it works. The work done pushing the magnet in against the opposing field is transferred to the electrical energy of the coil, of the induced current, and therefore energy is conserved. Okay, that's the end of the video. Make sure that you've made a note in your lab book of the formal statement of Lenz's law, and just practice it a little bit so that you can predict the direction of the induced current in different situations, like so.